Who's the class rep to your group? Class rep for your group? Yeah, the class rep. Complex analysis. Okay, can be the class rep. Are you online? Because I've been talking to your group, your group is a quiet group. You try to post anything, no one responds. Yeah, because I've posted to your group, we're supposed to have a class now. Now, no one is showing. Only 2 people I'm seeing on YouTube who are around. Yeah, so I'm starting the class. You can just join and talk to them later. Otherwise, I'm seeing 2. I don't know what it is, but I'm starting the class in around. This is the second time. Okay. Okay, good afternoon, students. This is a class for 3rd year complex analysis, which is MSM 341. So we are going to first start by looking at the complex number system. We are going to look at their complex, their basic definitions. We are also going to look at algebraic operations on complex numbers. I think we are going to look at it in phases. When we meet again, then we are going to look at other properties that involves complex numbers. Now, this is the first lecture on complex numbers. So this is how lecture 1 is being structured. We are going to look at the pure imaginary number and the complex number, so as being the definitions and some basic examples of the pure imaginary number and the complex number. Then we are also going to look at the algebraic operations on complex numbers, which are addition, subtraction, multiplication, and division. So now, if you look at, let's start by, when do we call a number to be a pure imaginary number? When do we call the number to be a pure imaginary number? Now, let's first look at this number. If you look at the square root of negative numbers, the square root of negative numbers, for example, the square root of -1, the square root of -4, the square root of -5, including the square root of -9. Not, these are just a few. These numbers, we call them a pure imaginary number. So now, if you remember, on SADs, under SADs, you can rewrite them. You can multiply SADs. That's what I think that was in first year. So any square root of any negative value, the value either being a fraction, being a decimal number, let me just say in general, whether a value is a rational number or rather a real number, provided it's the square root of a negative of that number, what we call that number, we call it a pure imaginary. So now the question is, I think in the first place, in first year you were saying, when you're looking at solutions to quadratic function, we used to say whenever the discriminant, which was under the square root, was negative, then the given quadratic equation does not have the real solutions. That means the type of solution that complex number has are complex. Now, let's try to go back to the sides. Again, we learned about sides. Now, look at this -5. You can also write it, for example, this is the square root of -5. Now, the -5, you can also write it as 5 times -1. Now, under sides, this is the square root of the product of two numbers. So this one you can also write it as, so in short, the square root of -5, which is just the same as the square root of 5 times -1. This is the same as, which is equal to the square root of 5 times the square root of -1. Also, the square root of negative 9, you can also write it as the square root of 9 times the square root of negative 1. Now, there's something which is appearing to be common. There's the square root of negative 1, which is multiplied to the square root of 9. Here also there's the square root of negative 1, which is multiplied to the square root of 5. So, for convenience purpose, we can introduce the symbol I. So, this symbol I, we are going to give it, we are going to replace it with where there is the square root of negative 1. So whenever we have the square root of 1, we have given it an I. Now, in this scenario now, we are going to say the square root of negative 5, which is equal to the square root of 5 times the square root of negative 1. Where there is negative 1, we are going to substitute an I. And also the square root of 9, negative 9, which is equal to the square root of 9 times the square root of negative 1, we are going to substitute where there is the square root of negative 1 by I. So then now, if you look at the square root of 9, the square root of 9 is 3. And then the square root of negative 1 is I. So in short, the square root of negative 9 is just equal to 3i as the standard form. So whenever you have the square root of a negative number, you just need to rewrite it to being the square root of that number times I, where I is the square root of negative 1. So now, let's look at where now we have something like the square root. Let's look at the value of the square root of negative 36. So the square root of negative 36, we can also write this as the square root of negative 9 times 4, which is the same as the square root of negative 9 times the square root of 4. Now, the square root of negative 9 is 3i, as it is appearing here. And the square root of 4 is 2. So 3i times 2, which will give us 6i. So which we have I've just explained here. But always remember that the square root of negative 9 times the square root of negative 4 is not the same as the square root of 36. The reason being is that the square root of negative 9 times the square root of negative 4, this is equal to, the square root of negative 9 is 3 times I, then the square root of negative 4 is 2 times I. Remember, I is the square root of negative 1. As such, this is going to give us 6 times the square of I. Now, if the square root of negative 1 is equal to I, then if we square I, what we're going to get is a negative 1. As such, this is going to give us a negative 6. So you should make sure that you take care of how the imaginary number is being affected by squaring it or by taking the square root of the product of the square root of the negative values. So this is about what we call a pure imaginary. So in this case now, so what we are saying is I is a pure imaginary. Because the square root of negative 1 is a pure imaginary, and remember the square root of negative 1 is equal to I. So the square root of negative 4 is equal to 2i. So the 2i is a pure imaginary number. Now, let's now look at when do we call a number to be a complex number. So if you combine a real number with a pure imaginary number, what you're going to get is what we call now a complex number. So in short, a complex number, a number of the form x plus iy. X, this plus iy, where the iy is a pure imaginary number. So when you have a pure imaginary number, just now remember that a pure imaginary number is a combination of a real number and an imaginary number. In short, you have the combination of a real number and the square root of negative 1. So that product of a real number and the square root of negative 1, which is I, so we call it a pure imaginary number. Now in this case, so there is this value y which has been multiplied by this I. So this type of a number which is written in this form x plus iy, where x and y are real numbers and I is just equal to the square root of -1 is called a complex number. Now, in this complex number, x plus iy, this x which is not multiplied to any I or any square root of -1, we call it the real part of this complex number. And the y which is multiplied by I, or rather which is multiplied by the square root of -1, we call it the imaginary part. It's part of the pure imaginary number. That's why we are calling it the imaginary part of the complex number. So in most cases, we denote this complex number by z. So generally, z is equal to x plus iy. Now, in this, if we have written this complex number as being z, which is equal to x plus iy, then the real and imaginary parts of z, which we have written as, so the real and imaginary part of this z, which I've written as x plus iy, the real part is x, the imaginary part is y, and we usually denote it by RE of z. So capital R then with small e. So this means the real part of z is equal to x, and for the imaginary part we use capital M then IM. So capital I then with M. So we say we are going to pronounce this as the imaginary part of z is y respectively. Now let's look at this example. Example number 3 is given. If it is an example on some complex numbers, which these are not the only complex numbers which are under consideration. There are a lot of complex numbers that you can think of, but this is just some of them, some of the examples of complex numbers. So the first one is the complex number -3 plus 5i. So -3 plus 5i, the real part is -3. So -3 is the real part of this complex number, and 5 is the imaginary part of the complex number. There's a difference between an imaginary number, a pure imaginary number, and also an imaginary part. An imaginary part is for a complex number. You know, a complex number is a combination of a real number and a pure imaginary number. Now, the pure imaginary number, that's why we pick the imaginary part of the complex number. So if I say 5i, then that is a pure imaginary number. But if I pick just a 5, this is called an imaginary part of the complex number. Also, we have 2 minus the square root of -36. 2 minus the square root of -36, we can also write it as 2 plus 6i. So in this case, 2 is our real part, and -6 is our imaginary part. In part 3, we have 5. Now, if you look at this, is just 5. Now, where is the imaginary part? We don't have the imaginary part. So, if you see this complex number as written in this form, where you are only able to see the real number, so this means the pure imaginary part is 0. The pure imaginary was 0. In short, this 5, we can also write it as 5 plus 0i, or I0. 5 plus I times 0. Then this means the real part will be 5, the imaginary part will be 0. That's why you are unable to see it. Also in part 7, we have 0, so this is 7i. Now this 7i, we can write it as 0 plus 7i. This is the same as 0 plus 7i. So in this scenario, the real part was 0, and then the imaginary part is 7. Now this is all about the complex number by being in its definition. So every number that is written in the form x plus iy is called a complex number. Now let's look at some algebraic operations on complex numbers. So let's look at some algebraic operations of complex numbers. Now, if you remember, last time we looked at SADs, that is in MSM 111, we looked at SADs. So the same scenario on how you add SADs is maybe before I even look at surds, let's try to look at the real number system. Remember, you can add, you can subtract, you can divide, you can multiply real numbers. Real numbers, including, what I mean is including the rational numbers, the natural numbers, and so forth and so on. Now, what about complex numbers? You can also add, subtract, multiply, divide complex numbers. Now, the way you handle in this case now is different from the way you handle it when you're dealing with when you're dealing with the real number system. These are complex numbers. So maybe if I can take you back to the way you add algebraic structures. For example, if I ask you to add maybe a plus b, then you add it to 3a plus negative 3b. So now you are going to add the like terms. You're going to add the like terms together. So even under complex numbers, basically you can add complex numbers. When you are combining them, you usually combine the real parts together and the imaginary parts together. So whenever you combine them, you should make sure that you bring it down to its simplest form. An example that has been given here is this 2 plus 3i. So if you look at this 2 plus 3i, you can't combine the 2 with the 3i. So there's this real part and the pure imaginary part of this complex number. So this complex number is already in its simplest form. You can't simplify it further. Now the question is, we are going to start with equal complex numbers. When do we go to complex numbers to be the same, to be equal? So two complex numbers, z, which is written in the form x plus iy, and w, which is equal to u plus iv, are equal. These two complex numbers are said to be equal, provided the real part of z and the real part of w are the same. Also, the imaginary part of z and the imaginary part of u are the same. Then you are going to call the two complex numbers z and w to be equal. So an example is, if 2 plus 3i is equal to x plus iy, this can only hold, this is only possible when x is equal to 2 and y is equal to 3. Then these two complex numbers are the same. Now, this is about two complex numbers which are equal. Then the question is, when can we add two complex numbers? How can we add two complex numbers? Okay, let's look at, this is part number 2, addition of complex numbers. So let's suppose we have two complex numbers, z, which is equal to x plus iy, and w, which is equal to u plus iv. If these are two complex numbers, then to add z and w, to add the complex number z and w, we add the real parts together and the imaginary parts together. From there, then you simplify. So you add the real parts together and the imaginary parts together. So this is the one we have written down here. So z plus w, remember z is equal to x plus iy, then plus w is equal to u plus iv. So you add the real parts. The real part of z is x, the real part of w is u, so this will be x plus u, then plus iy plus iv. Now the I is common, so this is the same as I times y plus v, which we have written here. You can factor out, you can factor out the I, and then you're going to have x plus u plus I y plus v. So you add the real parts together and the imaginary parts together. An example of this is given in example number 4, trying to clarify what we what the definition on addition of complex numbers is trying to tell us. So if you look at this example number 4, it's saying add the following complex numbers. Example number 4 is saying add the following complex number. The first Roman numeral number 1 is 3 plus 4i by 7 plus 2i. The second one is 1/5 plus 23i by 7 minus half of I. So they are asking us to add these two complex numbers in one and also the two complex numbers in part 2. So we are going to look at part 1 because part 2 is the same concept. So let's look at part 1. Now, to make it easy, or sometimes you can just go direct and add them, but now let's try to label these complex numbers. Let the first complex numbers be given by z. Let z be equal to 3 plus 4i and w be equal to 7 plus 2i. Then z plus w, remember z, we have given it to be 3 plus 4i, so it will be 3 plus 4i plus 7 plus 2i. Now the real part of z is 3, the real part of w is 3, so we add these two, so it will be 7 plus 3, 3 plus 7, then plus the imaginary part of z is 4i, then the imaginary part of w is 2i, so it will be now 4i plus 2i. Now 3 plus 7 is 10, 4i plus 2i is 6i. So this is our final answer, the addition of the complex number 3 plus 4i and 7 plus 2i. Similarly as in part 2, the concept is the same. The concept is the same. So when we assign, if we let z be equal to 1/5 plus 3/23i and w is equal to 7 minus half of i, then when we sum z and w, what we are going to get is 36 over 5 plus 45 over 2 multiplied by I, which is just the same concept. Now let's look at subtraction. When can you subtract? How can you subtract, in short, two complex numbers? Not when. How can you subtract two complex numbers? So if we have two complex numbers, z, which is equal to x plus iy, and w, which is equal to u plus iv, then to subtract them, the same condition for addition is also applied for subtraction. So we subtract the real parts together and the imaginary parts together. So you subtract the real parts together and the imaginary parts together. So same example that I'm going to use. This example, these same examples, example number 5 is similar to example number 4. The only difference is that in example number 5 we are subtracting, but it's the same complex numbers that I've used. So subtract the following complex numbers. Here we are saying you subtract 7 plus 2i from 3 plus 4i. The next one we are saying you subtract 7 minus half of I from 1/5 plus 23i. So let's label these complex numbers in Roman numeral 1. Let z be equal to 3 plus 4i and w be equal to 7 plus 2i. Then z minus w, which is equal to 3 plus 4i minus 7 plus 2i. So we are going to subtract the real parts together, which is here. It will be 3 minus 7i plus, and the imaginary parts together, 4i minus 2i. So 3 minus 7 to give us negative 4, 4i minus 2i to give us positive 2i. Now, is it possible that you can continue reducing this to something else? This is the only, this complex number is already in its simplest form. So we can't reduce it further. The only reduction that we can go as far as possible is factorizing, which is not even necessary when you reach at this stage. So this one is already in its standard form. So this one is already in standard form. So you don't need to go any further. So it's already in its simplest form. Similarly, the same concept that we have used here, you subtract the real parts together and also the imaginary parts together. We can also use them in part 2 of example number 5. It's the same scenario, just like when we're dealing with addition, which the answer is here. So when you subtract, if we let z be equal to 1/5 plus 23i and w is equal to 7 minus 1 over 2i, then z minus w, or what you're going to get is this complex number here. Now, if you look at this complex number here, it's already in its simplest form. So in short, it is in standard form. So you don't need to go any further more. You just end there, then it's done. Now let's look at so now before we go to the multiplication of complex numbers, let's look at powers, because multiplication sometimes it's all about the powers of a complex number. So now let's start with the power of I. This one is a very cardinal concept on complex numbers. We need to understand on powers of complex numbers, because we'll be solving equations that involves powers of complex numbers. So now let's look at powers of I, which is a complex, a pure imaginary number. Now remember, if I can remember, we had said I is equal to the square root of -1 from when we looked at the pure imaginary number in the beginning of our lecture. We said I is equal to the square root of -1. That's what we know. Now, what happens if we square both sides of this equation? This is more or less like an equation. I is equal to the square root of -1. What happens when we square both sides? When we square both sides, what you're going to get is the square of I is equal to -1. The square of I is equal to -1. Now, if the square of I is equal to -1, what happens if we multiply both sides of this equation, the square of I, which is equal to -1? Let's multiply both sides by I. Let's multiply both sides by I. So if you multiply both sides by I, what do we get? So it will be the cube of I. So in short, I to the power 3, this is equal to -I, because I squared times I, the bases are the same, so it will be I to the power 3. Now -1 times I to give us -I. So what we are saying is the square of I is always equal to -1, and I to the power 3 is equal to -I. Now, if we multiply both sides of this equation, I to the power -3 is equal to -1. Let's multiply both sides by I. So what we're going to get then on the left hand side, we're going to get I to the power 4. This is equal to I to the power 3 times I. But remember, I to the power 3 is equal to -I. So we are going to put -I here. So this will be -I times I. Using the associativity law, we are going to have -I squared. Now -I squared, negative the square of I. Now remember, the square of I is equal to -1. The square of I is equal to -1. Now negative times -1 will give us 1. So generally, I to the power 4 is equal to 1. So continuing with the same steps, let's multiply. So the equation that we have here is I to the power 4 is equal to 1. Now if you multiply both sides of this equation, what you're going to have is I to the power 5. Now I to the power 5, we can also write it as I to the power 4 times I. But I to the power 4 is equal to 1 times I. 1 times I is I. So I to the power 5 is equal to I. What of I to the power 6? Now from I to the power 4, this is where we need to now concentrate our understanding on. So let's look at I to the power 6. When you raise I to the power 6, this is the same as I to the power 4 multiplied by I to the power 2. Remember, when the bases are the same, you add the powers. But then I to the power 4 is equal to 1, but I to the power 2, which is this one, is equal to -1. What is 1 times -1? It will give us -1. So I to the power 6 is equal to -1. For I to the power 7, I to the power 7, we can also write it as I to the power 4 plus I to the power 3. I to the power 4, it will give us 1. I to the power 3 to give us -1. I mean -I, which is this one. Now 1 times -I is equal to -I. See how we need to look at the sequence of how the complex number behaves when you raise it to a natural number. I to the power 8 is the same as I to the power 4 times I to the power 4. I to the power 4 is equal to 1, I to the power 4 is equal to 1, 1 times 1 is equal to 1. What of I to the power 9? If you look at I to the power 9, I to the power 9, you can also write it with respect to I to the power 4. It will be like I to the power 4 times I to the power 5. But I to the power 5 is the same as I to the power 4 times I to the power 1. So you're going to have something like I to the power 4 times I to the power 4 times I. And I to the power 4 is equal to 1, another I to the power 4 is equal to 1 times I, which will give us I. So I to the power 9 is equal to I. So in general, so because I to the power 4 is equal to 1, because I to the power 4 is equal to 1, then I to the power 4 to the power n, this is index of an index, I to the power 4 to the power n is equal to 1 to the power n, because I to the power 4 is equal to 1, everything to the power n. And 1 to the power n number is 1. So I to the power 4 everything to the power n to give us a 1 for all integers n. Now, from this, thus it is possible, so from this scenario, we are able to see that it is very possible to evaluate powers of I by factoring out powers of 4. It is very possible to evaluate the powers of I by factoring out the powers of I to the power 4. An example is, let's look at I to the power 10. If you look at I to the power 10, this is the same as I to the power 4 times I to the power 4 times I to the power 2. So you first factor out the powers of I to the power 4, you first factor them out, and then you simplify. You try to reduce it in that manner. I to the power 10 is equal to I to the power 4 plus times story I to the power 4 times I to the power 2. I to the power 4 is equal to 1, I to the power 4 is equal to 1, I to the power 2 is negative 1. So I to the power 10 is negative 1. Now, from that kind of sequence that you have seen on how the powers of I behaves, we have this theorem. We have this general, we have this general theorem 6. So what this theorem is trying to tell us is, if n is a positive integer, then I to the power n, this is equal to I to the power r, where this r is the remainder of the division of n by 4. Is the remainder of the division of n by 4. So now, so if you look at this, what this theorem is telling us, no matter how big the power is, what you need to do to find the value of I, the power, that value, all you need to do is you divide first that value by 4, then you find your remainder. When you get your remainder, so I to the power that number is the same as I to the power, the remainder that you had found after dividing the power by 4. Let's look at these examples. Maybe before I come to this example, remember, whichever number, no matter how big the number is, when we divide it by 4, the remainder will either be 0 or 1 or 2 or 3. The remainder will never exceed 3. So no matter how big the number, you can think of any number, when you divide it by 4, the remainder can either be 0, or the remainder can be 1, the remainder can be 2, or the remainder can be 3. Let's try to go back to these powers. Let's look at first 5, I to the power 5. If you look at I to the power 5, if you say 5 divided by 4, 5 divided by 4, it will give us 1, remainder 1. 5 divided by 4 is equal to 1, remainder 1. Now, this means, I to the power 5, remember the remainder is 1. I to the power 5, this is equal to the same as I to the power 1. So I to the power 5 is equal to I to the power 1. Now I to the power 1 is I, which is the one which is here. So I to the power 5 is equal to I. Let's look at 6. when you divide 6 by 4, what you're going to get is 1 remainder 2. The remainder is 2. So I to the power 6 is the same as I to the power 2. 2 is the remainder. Now, I to the power 2 is equal to negative 1. That's why you're able to see here, I to the power 6 is equal to negative 1. Okay, now let's go to our example. So this example simplify the following. So they are asking us to simplify these powers of I. The first one is I to the power 36, the next one is I to the power 49, the last one is I to the power 86. Now, for I to the power 36, if we divide 36 by 4, we are going to get 9 remainder 0. So in short, 36 is the same as 4 times 9 plus 0. So in this scenario, our remainder is 0. So in short, I to the power 36 is the same as I to the power 4 times 9 plus 0. This is the same as I to the power 4 everything to the power 9 times I to the power 0. I to the power 4 is 1 to the power 9 and I to the power 0 is 1. So 1 to the power 9 is 1. So I to the power 36 is equal to 1. But instead of us writing all these things, even it's the same case in example in Roman numeral number 2. The easier way we can handle this is all you need to do is you divide this 36 by 4. 36 divided by 4 is 9 remainder 0. So in short, I to the power 36 is equal to I to the power 0. And any number to the power 0 is equal to 1. Here, 39 divided by 4, it will give us 12 remainder 1. So in short, I to the power 49 is the same as I to the power 1. And I to the power 1, it will give us 1. In the same scenario with 86. So this is about the powers of complex numbers. Now let's look at multiplication of complex numbers. How can we multiply two complex numbers? And what condition do we need to take to put into consideration as we are multiplying these complex numbers? Okay, now, if we have two complex numbers, z, which is equal to x plus iy, and w, which is equal to u plus iv, then to multiply them, remember, let me just take you back a bit. When you're adding complex numbers, you add the real parts together and the imaginary parts together. You add the real parts together and the imaginary part together, then you combine these two. Now, when you are multiplying these complex numbers, what we usually do, we just multiply them just as ordinary binomials. The way we multiply algebraic expression, remember, we multiply them across the board. We just multiply. Whether we are multiplying like terms or unlike terms, multiplication doesn't matter there. You just multiply. Now, after multiplying, then now we need to bring into consideration the fact that at the end of the day, after expanding, you need to add and subtract. That's why now you need to follow the conditions for additional subtraction. Where now add the real parts together and the complex parts together. I mean the imaginary parts together. So now, to multiply two complex numbers, z and w, we multiply the numbers as if they were ordinary binomials. So you just multiply them. You just multiply them as if they are ordinary binomials. We know what a binomial is. So now, and replace wherever there is I squared by -1. Whenever you see an I squared, replace it by -1. So an example is this one. Let's see. So z times w, this is equal to x plus iy times u plus iv. So this one expanding, this is the same as x multiplied by u plus iv, which is this one, plus iy multiplied by u plus iv, which is this one. So when we expand this part, what we're going to get is xu plus x times iv, then plus yi times u plus yi times iv. Now, simplifying this, before we even do the addition, simplifying, we are going to get xu plus ixv plus iyv plus I squared times yv. Now, look, this one, iy plus iy, remember I times I is I squared, then yv. Then, you see, This is xiv, this is plus yiv. These are imaginary, pure imaginary numbers. So now we have reached this stage. This is the stage, maybe let's simplify this one. This I squared is equal to -1. So -1 times yv to give us negative yv. So we are going to have xu plus ixv plus, xu plus ixv plus iyv minus yv. So at this stage then, you collect the real parts together and the imaginary parts together. So you're going to add the real parts together and the imaginary parts together. But when you're multiplying, you just multiply them across the board. Now when it comes now after when you have done the multiplication, when you have already expanded, then when adding or subtracting now, that's when now you need to remember those restrictions. You add the real parts together, you also add the imaginary parts together, which is just giving us this. So you have xu plus ixv plus iyv minus yu minus yv. So the minus yv is a real number, xu is a real number, xv is an imaginary part, yu is an imaginary part. So we add these together and also the real parts together, which is giving us this value here. So we are going to have xu minus yv plus ixv plus yu. So now example number 8. Let's look at example number 8. Multiply each of the two complex numbers. The first one is you are multiplying 3i by 2 minus 5i. Now if you look at example number 8, part Roman numeral 2 and 3, these same numbers, these same concept numbers, I've used them under addition and subtraction. And also I've brought them down so that you could see how the difference between addition, subtraction, and multiplication. Now, let's start with the first one, then I'll come to the second one. The third one, you can just look at it, the solution is there in the notes. So now, let our z be equal to 3i and our w be equal to 2 minus 5i. Then z times w, this is equal to 3i times 2 minus 5i. So you multiply this 3i by 2, and then you multiply this 3i by negative 5i. So 3i times 2, we are going to get 6i. Then 3i times negative 5i, we are going to get 15i squared. Now, this I squared is equal to -1. So this is the same as 6i minus 15i times -1, which will give us 6i plus 15i. So writing it in standard form, we are going to have 15 plus 6i. Then you are done with the multiplication of these two numbers. Let's go to the next one. The next one is, this is the solution is continuing. Now, in part 2, we let z be equal to 3 plus 4i and w be equal to 7 plus 2i. Then, the product of these two, this is the same as 3 plus 4i times 7 plus 2i. So, this is the same as 3 times 7 plus 2i plus 4i times 7 plus 2i. When we expand this, we are going to have 3 by 7 to give us 21, 3 by 2i is going to give us 6i, 4i times 7 it's going to give us 28i, 4i times 2i is going to give us 8i squared. Now the I squared is equal to -1, which is here. So the 26i plus 28i it's going to give us the 34i. Then the 21 minus 8 is going to give us the 13. So in short, 3 plus 4i multiplied by 7 plus 2i is going to give us 13 plus 34i. In the same manner, we can add 1/5 plus 3i and 7 minus half of I, and then we are going to get the answer, which is here. Okay, now let's go to the conjugate of a complex number. Remember, before looking at multiplication, we looked at powers of complex numbers. So before looking at division of two complex numbers, let's look at the conjugate of a complex number. You have this complex number, and then you have its conjugate. You are given this complex number. how does its conjugate, what is the structure of its conjugate, complex conjugate? Okay, now, what is really the difference between the given complex number and its complex conjugate? The only difference which is there is the sign in the imaginary part. So two complex numbers which differ only in the sign of the imaginary parts are called conjugate of each other. So if you have this complex number, the sign is either positive or negative. So there is this difference between their imaginary parts. So if these two complex numbers, the only difference they have is the sign of their imaginary parts, then those two complex numbers, we call them the complex conjugate of each other. So an example, if the complex number z has been given as x plus iy, then the complex conjugate of the complex number z, which we denote by z bar, we put bar on top, which is like z, we put a bar on top. So this number is the complex number z bar, which is equal to x minus iy. Now look at the difference between z bar and z. The only difference they have is the sign in their imaginary part. Here we have positive y, here we have negative y. That's the only difference between these two. Now an example is 2 minus 3i. The complex conjugate of this complex number 2 minus 3i, its complex conjugate is 2 plus 3i. So in short, what I'm trying to say, either way, we are going to say 2 minus 3i is the complex conjugate of 2 plus 3i. You can even do it the opposite. You can even say 2 plus 3i is the complex conjugate of 2 minus 3i. It's one and the same thing. And the complex conjugate of negative 3 minus 4i, its complex conjugate is negative 3 plus 4i. The only difference that they need to have is the sign in their imaginary parts. So now, what is so important about this complex conjugate? The concept of complex conjugate is very important in that it usually helps us to switch from complex to real. It helps us to switch from complex to real numbers and from real numbers to complex numbers. Now, let's look at this theorem, which is helping us on how to switch. You have this complex number, how can you make it to be a real number? Let's look at this theorem. This theorem says that the sum and product, if you multiply a complex number and its complex conjugate, excuse me, or if you add a complex number and its complex conjugate, what you get is a real number. But if you subtract a complex number and its complex conjugate, what you're going to get is a complex number. Let's look at the proof. If our complex number is x plus iy, then its complex conjugate is x minus iy. Now, if we add x plus iy by x minus iy, remember, x plus x, it will give us 2x, positive iy minus iy to give us 0. So in short, you're going to have 2x. If you look at this 2x, there's no pure imaginary number that has been multiplied to it, or there's no I which is multiplied to this 2x. So it's totally a real number. And the product, if you multiply x plus iy by its complex conjugate x minus iy, this is the difference of two squares in short. So this will be x squared plus iy squared. Now x squared plus, remember, y is not a pure imaginary number. Y is an imaginary part of a complex number. So you should know that, you should make sure that you remember that. So now this will give us x squared plus y squared. X is real. The square of a real number is a real number. Y is a real number. The square of a real number is a real number. So the sum of two real numbers is a real number. this example is just trying to clarify what this theorem is saying and the proof. So you can just look at it and see that this holds. The theorem is generally satisfied by this example. Then let's also look at some of these properties that involves the complex conjugate and the complex conjugate of a given complex number. So now, for the real part x and imaginary part y, not iy. Remember, iy is not the imaginary part, that is a pure imaginary number. But y is the imaginary part. So for the real part x and the imaginary part y of any complex number z, which is equal to x plus iy, these properties hold. These properties hold. The real part of z is equal to 1 over 2 times z. Oh, the real part of z is half of their sum of z and its complex conjugate. Half of the sum of z and its complex conjugate, it will give us the real part of z. Also, 1 over 2i multiplied by the difference of z by its complex conjugate, what you get is the real part of z as well. Now, if z, I think we need to look at this scenario. I think it was supposed to be imaginary part of z, because we're going to have x plus iy minus x minus iy. So we are going to have 2iy. So this one, it was supposed to be the imaginary part of z, not the real part of z. You can just take note of that, which is theorem number 10. So I'm going to look at it and then I'll make some changes. Okay, now, also, if you have two complex numbers, z1 and z2, then the conjugate of their sum, this is equal to the sum of their conjugate. The conjugate of the sum of z1 and z2 is equal to the sum of the conjugate of z1 and the conjugate of z2. On their difference is also the same. So now from this, you can prove this. These are basic properties of complex numbers that you can prove. You can just assign the structure of z1 and also z2. You can even say let z1 be equal to x1 plus iy1 and z2 be equal to x2 plus iy2. Then you can compute the right hand side and also the left hand side. You're going to realize that they will be the same. Then let's now look at division. Division and multiplication are similar. So if we have two complex numbers z, which is x plus iy, and w, which is u plus iv, then to divide them, now, if you want to divide these two complex numbers, what you need to do is you are going to multiply both the numerator and the denominator of the fraction by the complex conjugate of the denominator. And then you replace wherever there is I squared by -1. Reason being, if you write z divided by w, which is equal to x plus iy over u plus iv, then provided there is a pure imaginary which is appearing in the denominator, this complex number is not in its standard form. So to write it in its standard form, we need to multiply both the numerator and the denominator by the complex conjugate of the denominator. Now our denominator in this case is u plus iv. Its complex conjugate is u minus iv. So when we multiply the numerator and the denominator by the complex conjugate of the denominator, there's nothing really, the quantity is the same. This value is the same as this one. There's no difference. Then when we do the multiplication and simplify, after we do the multiplication in the numerator, multiply x plus iy by u minus iv, and also in the denominator we multiply u plus iv times u minus iv. Remember, this in the denominator we have a difference of 2 squares. This will be a difference of 2 squares. So when we simplify and evaluate, what we're going to get is xu plus yv over u squared plus v squared. U squared plus v squared is not a complex number. This is a pure real number. Plus I uy minus xv over u squared plus v squared. So z divided by w, it will give us this value which is here. Now let's look at some examples. The same example, let's look at example number 11, which is trying to clarify on the division of two complex numbers. Let's look at example number 11, which is clarifying on the division of two complex numbers. Now, divide 3 minus 6i by 2i and also 1 plus I by 3 plus 4i. So in this case, let's label this in part 1, let's label the 3 minus 6i and the 2i. Let's name this one to be equal to z. What I'm saying is let z be equal to 3 minus 6i and w be equal to 2i. Then z divided by w, which is equal to 3 minus 6i over 2i. Now you see, if you look at 3 minus 6i divided by 2i, this is not in standard form. Standard form was supposed to appear like a plus ib. Now this complex number is not in standard form, so we need to reduce it to a standard form. How can we do this now? So like in this case, we can multiply the numerator and the denominator by I. Definitely it will convert the denominator to a real number. So division, what division does is you need to make sure that the denominator is not a complex number. It should be some real number. That is our goal here. So now, if you look at this, when you multiply both the numerator and the denominator by I, so 2i times I to give us 2i squared, then we have 3 minus 6i multiplied by I, so this will give us 3i minus 6i squared. Now, remember, the square of I is equal to -1, and also the square of I in the numerator there, which is multiplied to 6, is equal to -1. So we're going to have 3i minus 6 times -1 over 2 times -1, which will give us 3i plus 6 over -1. Then this one, when you divide through each term by 2, what we're going to get is -3 minus 3 over 2i. This one now is in standard form. And our real part in this case is -3, and our imaginary part is -3 over 2. Then we have simplified our complex number, the division of these two complex numbers. For the next one, we let z, in part 2, we are going to let z be equal to 1 plus I and w be equal to 3 plus 4i. Now, in this case, what we are going to do is, when we divide these two, we are going to have z divided by w, this will give us 1 plus I divided by 3 plus 4i. So now, because we're able to see some complex number in the denominator, the only way we can do this is we multiply both the numerator and the denominator by the complex conjugate of the denominator, which is we have done here. Our denominator is 3 plus 4i. Its complex conjugate is 3 minus 4i. This means we multiply both the numerator and the denominator by 3 minus 4i, which is the one which is appearing here. So now when we expand, we multiply these two, what we are going to get is 1 plus I multiplied by 3 minus 4i. We're going to get 3 minus 4i plus 3i minus 4i squared. Simplifying this, we are supposed to get, if we simplify this, we are supposed to get a set, because this was I squared, so it will be -1 times -4 to give us 4 plus 3 to give us a 7, and then -4i plus 3i to give us a -i. So we are supposed to have 7 minus I divided by 25. So then when we split this, it's going to give us 7 over 25 minus 1 over 25i. So this one now is in its standard form. Then, now, so this is all about the basic properties of complex numbers and also the algebraic operations on complex numbers, which we have seen the power rule, we have seen the division, multiplication, addition, and subtraction, including the conjugateness. So all these are operations on complex numbers. So let's look at another example which involves division. So there is this example number 12, which is also it's a combination of division and multiplication. So in this case, they are saying, example number 12, you simplify this complex number, which is 5 minus 3i multiplied by 7 plus I over divided by 2 minus I, and write your answer in the form a plus ib. So what you are saying is you simplify this complex number to its simplest form, and then you write your answer in standard form. So now here there are about two things involved here. There is multiplication and division involved at the same time. So when you are dealing with such kind of a scenario, what you need to do is first simplify. If this is the case, simplify the numerator. Don't start by multiplying both the numerator and the denominator by the complex conjugate of the denominator. That will mean your work will be tedious. So what you need to do here is first simplify the numerator. By simplifying the numerator, what I mean, deal with the product first, which is in the numerator. So you deal with the product 5 minus 3i and multiply by 7 plus I. After dealing with it, you write the numerator in standard form. From there now, that's when now you can multiply both the numerator and the denominator by the complex conjugate of the denominator. So when you multiply the two complex numbers which are in the numerator of this complex number, what you're going to get is the 38 minus 16i. So it will be 38 minus 16i divided by 2 minus I. Now I've not dealt with the denominator. We've just let the denominator be the way it is. Then after reaching at this, in this case now, after reaching at this level, then now you're able to see that, okay, the denominator is in standard form, the numerator also is in standard form. From this now, that's when now you can think of now, you can say, you now multiply both the numerator and the denominator by the complex conjugate of the denominator, which is the 2 plus I. So what I'm saying is, you see, this 5 minus 3i multiplied by 7 plus I divided by 2 minus I, this is the same as 38 minus 16i divided by 2 minus I. So then, to simplify this complex number, we can multiply both the numerator and the denominator as at this stage by the complex conjugate of the denominator, which is this, which is here. And the complex conjugate of the denominator is 2 plus I. Then after simplifying both the numerator and the denominator, we simplify these products. What we are going to get is a 92 plus 6i divided by 5. Then we split this to give us 92 over 5 plus 6 over 5i. So what we have written, this expression is in the form a plus ib, where our a is 92 over 5 and our b is 6 over 5. So this is all about complex numbers simplification with respect to the algebraic operations on complex numbers. So now this is the end of this. We have references. These are some of the textbooks that you can use for your own reference purpose. And also this is the end of lecture 1 on complex numbers. So when we meet again, should be on Thursday or Friday, that one according to our timetable. We are going to look at lecture number 2, where we will look at other structures, other properties on complex numbers. Thank you for listening, and have a lovely afternoon.